Over the past 6 weeks, the seafloor off America's west coast has been unusually noisy. On June 3rd, a magnitude 5.7 struck about 140 miles off the southern Oregon coast. The same day, a magnitude 5.1 and a cluster of magnitude 4 class shocks rattled the waters west of Petrolia, California, at the notorious corner where 3 tectonic plates meet. Then, at the end of June, another burst, a magnitude 5.5 more than 200 kilometers west of Bandon, Oregon, wrapped in its own swarm of smaller events. And in early July, a magnitude 3.8 popped off beneath Puget Sound itself near Oak Harbor, Washington, at a depth of 25 kilometers deep under the inland waters north of Seattle. 17 earthquakes of magnitude 3.5 or greater in under 2 months, strung along the coastline of Northern California, Oregon, and Washington. But here is the twist, and it is the reason this video exists. Those earthquakes, the ones you can feel, the ones that make the news alerts, are not the strange tremors in this story. The strange ones are happening right now, and you cannot feel them at all. Deep beneath the Pacific Northwest, at depths of 25 to 40 kilometers, instruments have been recording a kind of shaking that science did not even know existed until this century. A shaking that arrives in episodes lasting days to weeks. A shaking that releases as much energy as a magnitude 6 or 7 earthquake, in total silence, while millions of people above it feel nothing. It returns on a schedule, roughly every 14 months, like clockwork, and every single time it does, it slightly increases the load on the giant locked fault offshore, the Cascadia subduction zone, the one capable of a magnitude 9. When scientists finally figured out what this silent shaking was, it rewrote textbooks, and it may one day rewrite something far more important. The warning time before the biggest earthquake in American history. Today, the full story of what scientists found deep below the West Coast. No guessing, no dramatizing. Just the facts, the science, and the real stakes. Quick word before we go deep. If you live anywhere along this coastline, Northern California, Oregon, Washington, British Columbia, drop a comment and tell me where and whether you felt any of the offshore shocks these past weeks. Because reports from the ground are part of how this community tracks these events together. And if you want to follow this fault system as the science develops, subscribing is the simplest way to stay connected. It is free, and this channel covers this coastline constantly. Now, down we go. Start with the earthquakes you can feel, because they set the map. The burst of activity off Oregon these past weeks, the magnitude 5.7, the 5.5, the string of magnitude 4s west of Bandon and Port Orford, almost all of it traces to a single structure most people have never heard of, the Blanco fracture zone. The Blanco is a transform fault, a strike slip, boundary like a miniature offshore San Andreas, connecting 2 spreading ridges on the seafloor, and it is, by raw count, one of the most seismically active features anywhere near the continental United States. It produces swarms like this routinely, several magnitude 5 class events in a typical year, because its young, hot oceanic crust breaks easily and often. Farther south, the cluster west of Petrolia sits at the Mendocino Triple Junction, the tectonic 3-way intersection where the Pacific Plate, the Gorda Plate, and the North American Plate all meet, the single most seismically active spot in the lower 48 states, and the place that produced a magnitude 7.0 as recently as December 2024, an event that briefly triggered tsunami warnings for millions before the all clear. And the small, deep event beneath Puget Sound belongs to a third family entirely, an intraslab earthquake, a snap inside the ocean plate that has already dived beneath Washington, the same family as the magnitude 6.8 Nisqually earthquake that damaged Seattle in 2001. 3 different mechanisms, 1 coastline, 6 weeks. And here is the honest sentence about all of it, delivered up front, the way this channel always does. None of this felt activity is abnormal, and none of it, by itself, signals that the big one is coming. The Blanco swarms in particular, despite the scary headlines they generate every single year, occur on a fault that is mechanically separate from the great offshore megathrust, and does relatively little to load it. If this video were only about those earthquakes, it would be a short video. But those earthquakes are the surface noise. The real story is the signal underneath. And to tell it, we have to go back to the summer. A scientist noticed something impossible. In the late 1990s, geodesist Herb Dragert was doing patient, unglamorous work, watching a network of GPS stations planted across Vancouver Island and the Pacific Northwest, stations precise enough to track the slow bending of the continent as the offshore Cascadia fault, locked tight since the year 1700, dragged the coastline eastward, compressing it like a spring, exactly as the textbook said it should. Millimeter by millimeter, year after year, every station crept in the expected direction. And then, over a stretch of days in 1999, a cluster of stations stopped, turned around, and moved the other way. Westward, backward, as if a piece of the fault somewhere deep below had quietly slipped and let a sliver of the stored spring relax. No earthquake had been recorded. No shaking had been felt. The ground had simply silently moved, and then, after about 2 weeks, the stations turned around again and resumed their normal eastward creep as if nothing had happened. Draggart and his colleagues had discovered what we now call a slow slip event, an earthquake in slow motion, a fault patch slipping the same distance it would slip in a real earthquake, but taking 2 weeks instead of 30 seconds, releasing its energy so gradually that it produces no shaking a human being can feel. When they went back through the records, they found these silent events were not rare. They were regular, repeating beneath the Puget Sound and Vancouver Island region, roughly every 13 to 14 months, each one releasing the energy equivalent of a magnitude 6.5 to 7 earthquake. For comparison, the Nisqually earthquake that injured hundreds and did billions in damage in 2001 was a 6.8. Events of that energy scale had been occurring under the region's feet on a schedule for as long as anyone could reconstruct, and nobody in human history had ever noticed. Then came the second half of the discovery from the other side of the Pacific. 2002. Japanese seismologist Kazushige Obara, studying data from Japan's dense network of borehole seismometers above their own subduction zone, the Nankai Trough, identified a bizarre signal, a faint, continuous low-frequency rumble rising out of the deep plate boundary, not the sharp crack of an ordinary earthquake, but something more like a distant train, or a vibration going on for hours, days, weeks. He called it deep, non-volcanic tremor, and no one knew what it was. The breakthrough came a year later, back in Cascadia, when seismologist Gary Rogers and Draggart put the two mysteries side by side and found they were the same mystery. Every time the GPS stations reversed, the tremor switched on. Every time the silent slip ended, the tremor faded. The slow slip and the strange rumble were two voices of a single phenomenon, which they named episodic tremor and slip, ETS, and it has since been found at subduction zones around the world: Japan, Mexico, New Zealand, Alaska, Costa Rica. This is what the title of this video means. What scientists found deep below the west coast is a second kind of earthquake, a whole hidden regime of fault behavior operating continuously beneath one of the most heavily populated corridors in North America, invisible to every instrument humanity possessed until about 25 years ago. So what is actually happening down there? Here is the science engine, in plain language. Picture the Great Cascadia Fault as a ramp, the ocean plate sliding down beneath North America, and picture that ramp divided into zones by depth and temperature. The shallow part, offshore, from the seafloor down to around 20 kilometers, is cold and cold rock grips. That is the locked zone, the section that has been stuck since January 1700, storing 3¼ centuries of strain, the section that will one day rupture in minutes and produce the magnitude 9 and the tsunami. The deepest part, below about 40 kilometers, is hot enough that the rocks flow like extremely stiff taffy, sliding steadily and silently forever, no earthquakes at all. And in between lies the strange Middle Kingdom, 25 to 40 kilometers down. Too warm to stay locked for centuries, too cold to flow smoothly and soaked in water, fluids wrung out of the descending ocean plate as heat and pressure cook its minerals. That trapped pressurized water is the key. It pushes the fault surfaces apart ever so slightly, weakening their grip, and the result is a fault that can neither hold on nor let go cleanly, so it stutters. Every 14 months or so in Cascadia, the middle zone loses its grip and slips a few centimeters over days to weeks. And as it slips, millions of tiny stick and slide failures crackle along it, merging into that continuous rumble, the tremor, the fault literally humming as it moves. Seismologists can now track the humming in real time, watching bands of tremor ignite near Puget, sound and migrate along the coastline at a few kilometers per day, mapping the silent slip as it travels. The Pacific Northwest Seismic Network logs thousands of tremor bursts during a single episode, and anyone, including you, can watch the maps update online while feeling absolutely nothing in their kitchen. It is one of the most extraordinary monitoring capabilities in all of Earth science, a live feed from a part of the planet that was complete darkness a generation ago. Now for the part that turns a scientific curiosity into one of the most consequential questions in American geology. Every slow slip event moves the deep fault a few centimeters, but the shallow fault above it, the locked zone, does not move, which means every episode transfers a small amount of additional stress upward onto the exact section that will one day produce the great earthquake. 14 months at a time, tick by tick, the silent events are loading the gun, and that arithmetic leads to a hypothesis that scientists discuss with great care and take completely seriously. If a slow slip event adds stress to a locked zone that is already, after 325 years, near its breaking point, then the probability of the great rupture, while always low on any given day, should be slightly higher during an ETS episode than between them. The window hypothesis. It has real support. Careful studies in Japan concluded that the catastrophic 2011 Tohoku earthquake was preceded in its final weeks by slow slip migrating toward the eventual epicenter, and similar slow precursors have been reconstructed before other great subduction earthquakes, including the 2014 Iquique event in Chile. Japan has gone furthest with the implications. Its megaquake advisory system, the one that raises official probabilities after unusual activity near the Nankai Trough, exactly the protocols this channel covered in our Japan episodes, is built partly on the science. And here comes the honest pivot, delivered with both hands. No slow slip event anywhere on Earth has ever yet been used to successfully predict a great earthquake in advance. Cascadia has produced roughly 20 ETS episodes since discovery, and the megathrust has not ruptured during any of them. Most slow slip events, overwhelmingly, are followed by nothing at all. The window hypothesis says the odds during an episode might rise from something like 1 in 10,000 on a given day to a few in 10,000, a real change, a meaningful one for emergency planners, deciding when to run drills, and still an overwhelming likelihood of nothing. Anyone who tells you the next Tremor episode is a countdown is lying to you. What the science actually offers is subtler and, in the long run, possibly far more valuable. For the first time, we can watch the deep fault move. If a future slow slip event behaves differently, if the tremor migrates toward the locked zone instead of along it, if the slip is larger, faster, shallower than any episode on record, the instruments will see it within hours, and the scientists watching those screens have said openly that such an anomaly would be treated with the utmost seriousness. It is not prediction. It is the closest thing to a stethoscope on the chest of a magnitude 9 fault that our species has ever possessed. And that stethoscope matters because of what it is listening to. We covered the full Cascadia scenario in a previous episode, the last rupture on January 26, 1700, dated to the evening. By the orphan tsunami it sent to Japan, the ghost forests of drowned trees still standing on the coast, the 1 in 3 odds of a significant Cascadia earthquake in the next 50 years, the shaking of 3 to 6 minutes, the tsunami arriving in tens of minutes, the months without power. If you have not seen that episode, it is the essential companion to this one. It is worth adding one thread that episode could only touch, because it belongs to this story of listening. The instruments were not the first to hear this coastline. The indigenous nations of the Pacific Northwest carried the 1700 earthquake in their oral traditions for 3 centuries before science confirmed it. Stories passed generation to generation among the Maka, the Ho, the Quileute, the Huayat, and many others, of a winter night when the earth shook long and the sea came into the villages, of canoes left in trees and settlements that vanished. When researchers finally referenced those accounts with the Japanese tsunami records and the tree rings of the ghost forests, they matched. The first monitoring network on this fault was human memory, and it worked. It preserved the warning for 300 years, waiting for someone to take it seriously. What this discovery adds to that picture is the beginning of an answer to its most terrifying feature, the suddenness. A fault that has been silent for 3 centuries offers a population nothing to react to. A fault whose deep half hums every 14 months offer scientists a rhythm, and rhythms can break in informative ways. The tremor catalogs are still young, 25 years, against a 700-year earthquake cycle, and the researchers are the first to say they do not yet know which changes in the pattern would matter. But somewhere, in those humming records, very possibly, is the signature that will one day precede the rupture, and the only way to recognize it then is to record everything now. That is what the ocean bottom sensors going onto the seafloor are for, what the borehole stations drilled along the coast are for, what 2 nations' worth of monitoring budgets are quietly buying. A chance, not a promise, that the great earthquake of the Pacific Northwest becomes the first magnitude 9 in human history to be seen coming. Before the practical message, 2 more layers belong in this story, and the first is a confession on behalf of the entire monitoring effort, because there is a blind spot in everything I have described. And it happens to sit exactly over the most dangerous part of the fault. Think about how the discovery was made: GPS stations on land, seismometers on land, all of it on land. But the locked zone of Cascadia, the section storing the magnitude 9, lies offshore under the Pacific, 40 to 100 miles from the nearest coastal instrument. GPS does not work underwater. Radio signals cannot penetrate the ocean, which means the very technique that revealed slow slip in the deep zone is nearly deaf to whatever the shallow locked zone is doing right now. Is the locked section fully locked, storing every millimeter of strain? Is it partially creeping, quietly bleeding off some of its debt? Are there slow slip events out there too, on the shallow end, in the years or days before rupture? The kind Japan reconstructed before Tohoku? For most of Cascadia, the honest answer is that we do not fully know, and closing that gap has become one of the great engineering pushes in earth science. Ocean bottom seismometers now sit on the Cascadia seafloor. listening where land stations cannot. Pressure sensors on the abyssal plain can detect the seafloor itself lifting or dropping by centimeters, exactly what a shallow, slow slip event would produce. Seafloor geodesy, one of the most delicate measurements humans attempt, uses acoustic transponders on the ocean floor, interrogated by ships and autonomous surface drones, to track the position of the seabed itself to within centimeters, GPS for a place GPS cannot reach, and cables laid across the ocean floor, including scientific cabled observatories off Oregon and Vancouver Island, stream data back to shore in real time from instruments parked directly above the sleeping rupture zone. Japan, after 2011, wrapped its own trenches in exactly this technology, a vast cabled sensor net called S-net, precisely because Tohoku taught them that the ocean was where the warning had been hiding. Cascadia's version is still being built out, sensor by sensor, budget cycle by budget cycle, and the scientists pushing it make the stakes plain. The deep tremor we can hear is the fault's heartbeat. The offshore locked zone we still hear poorly is its trigger finger. The race is to finish wiring the ocean before the ocean finishes the countdown no one can see. The second layer is the world tour, because Cascadia's silent earthquakes turned out to be one member of a global family, and every relative teaches us something the Northwest cannot learn about itself. In Mexico, beneath the state of Guerrero, the subduction zone produces some of the largest slow slip events on Earth, silent movements equivalent to magnitude 7.5, lasting months, directly beneath a stretch of coast called the Guerrero Gap that has not broken in a great earthquake for over a century. And researchers there documented a disturbing sequence. A large, slow slip event was in progress in the region in the weeks before the deadly 2017 earthquakes, sharpening the global question of when silence enables violence. In New Zealand, the Hikurangi margin off the North Island produces slow slip so shallow, just a few kilometers beneath the seabed, that scientists have done something impossible anywhere else. They sailed a drilling ship out and bored directly into the slow slip zone, planting instruments inside the fault itself and recovering the actual rocks that stutter, clay-rich. Water-soaked, exactly the materials the theory predicted. In Japan, beyond discovering tremor in the first place, the dense networks have mapped the entire zoo of slow behavior, and it is a genuine zoo. Low-frequency earthquakes, the individual crackles inside the tremor. Very low-frequency earthquakes, slow ruptures lasting tens of seconds, short, slow slip. Events lasting days, long ones lasting years, put the whole family together, and a profound reframing emerges, one that has quietly revolutionized how scientists think about faults. Earthquakes come in speeds. At one end of the spectrum, ordinary earthquakes, rupture racing at 2 miles per second, all the energy in seconds, shaking, destruction. At the other end, steady, silent creep, the fault sliding smoothly forever, no events at all. And in between, filling in what was once thought to be an empty gap, the slow earthquakes, days long, weeks long, years long, each speed produced by its own recipe of temperature, pressure, rock type, and above all, water. The fault is not a switch that is either off or exploding. It is an instrument with a full range of voices, and the deadly fast rupture is simply the loudest note it can play. That reframing matters practically because it means the boundary between slow and fast is a physical condition, not a category, and conditions can change. The nightmare and the hope of this entire field live in the same sentence. Somewhere, someday, a slow event will cross the line and become a fast one, and the instruments will have been watching it happen. Every tremor episode Cascadia records, every drilled core from New Zealand, every silent Mexican giant is a page in the manual for recognizing that moment, a manual being written in real time by a science that is younger than the people watching this video. The practical message, as always, does not wait on the science. If you live in the Pacific Northwest, the preparation picture has not changed and will not change. 2 weeks of self-sufficiency, water, food, medications, because the honest planning documents say help will be slow in the scenario that matters. Secure the house, know the gas shutoff, keep sturdy shoes and a flashlight reachable from the bed, and burn in the one rule that outruns every warning system. If you are on the coast and the ground shakes hard or long, you do not wait for sirens or phones. The shaking is the warning, and you move inland and uphill immediately on foot if the roads are jammed, because the tsunami can arrive inside 20 minutes, and the people who move first are the people the statistics call survivors. The tremor science may someday buy this, region hours or days of official caution. The kit in your closet and the route in your head are what turn any warning, long or short, into a life saved. And one more suggestion, this one just for the curious. The tremor maps are public. The Pacific Northwest Seismic Network publishes them openly, updating as episodes ignite and migrate, and there is something genuinely grounding about pulling up that map during the next episode and watching the deep fault hum beneath your own region in real time, knowing what you now know about what that humming is. Fear thrives on the invisible. The map makes it visible, Invisible things can be lived with, planned for, and respected without panic. Here's the closing thought, and tonight it is a quieter one. Somewhere beneath Puget Sound, 25 miles down, in rock no human eye will ever see, the deep edge of the Cascadia Fault is doing what it has done every 14 months, for longer than our civilization has existed, slipping, humming, whispering into the dark. For all of human history on that coastline, from the first peoples whose oral traditions still carry the memory of 1700 through every city built since, that whisper went unheard. Not ignored, unheard, unhearable. And then, within a single generation, patient people with careful instruments taught themselves to listen, and the silence under the west coast turned out to be full of voices. The fault has been talking this whole time. We are the first generation that can hear it, and the scientists at those screens, tonight and every night, are listening on behalf of everyone who sleeps above it. Whatever the fault says next, this channel will be following, carefully and honestly, as the story develops. If tonight's journey deep below taught you something, tell me in the comments what surprised you most. I read them, and the conversations there are becoming one of the best parts of this work. Until the next one, take care of yourselves, look after the people around you, and sleep well knowing that someone is listening to the deep. See you soon.